Hello again. So this is the last session for the year, and in it we're going to take a look at the binomial expansion, otherwise called the binomial theorem. There are plenty of worked examples in your exercise book for you to look at as well, and there are some quite tricky problems for you to tackle if you're willing to give yourself a bit of a challenge. Do be careful, you've got to keep very careful track of everything when you're doing these examples, and be especially careful when you've got negative numbers involved. So I hope you enjoy the challenge of the problems and that it starts becoming familiar to you. You will need your calculator for this unless you're willing to draw out lots and lots of lines of Pascal's triangle. And in case I don't get to see you before Christmas, then I'd like to wish you a very merry festive season, and especially have a wonderful 18th birthday, and I'll see you in the new year. Goodbye then.
Okay, so we're going to take a look at the binomial theorem, that's sometimes referred to as the binomial expansion. It really doesn't matter which you choose, and this may well be familiar to you already, so it might just be a bit of a recap. So let's get started. Right, so the first thing I want you to do is to do a bit of work. We did expand in brackets before, so I want you to either write down, if you know them, or work out these expansions. So a plus b squared, a plus b cubed, and a plus b to the 4. Okay, so I want you to take your time to work out those expansions and have them written down, and I also at the same time want you to state what a plus b to the power of 1 is and what a plus b to the power 0 is. Okay, just pause this now and take your time to just write those answers down for me. Okay, so hopefully you pause the tape, look how old I am. Hopefully you pause this recording and you've got those answers down. Let's just double check here before we go on to look at the other things. Anything to the power of 1 is just itself, so this is just a plus b, and I hope you all remembered that anything raised to the power of 0 is simply 1. So let's look at the answers then, and I've written these out in a specific way. So let's have a look. Here we go. So here's my answers, and you can see I've written them out in a certain way, and I've also highlighted the coefficients here in red. Now I know I'm forever telling you, if you do in algebra and you end up writing 1x or 1y, that you don't need the 1, and that is perfectly true. But what I'm going to do is I'm just going to put these ones in. So 1a, 1b, 1a squared, because this just makes everything clearer. So I hope if you look now at the pattern of red that you actually recognise this, and you may not remember the name of it, but it's these coefficients are Pascal's triangle, and I'm sure you can either remember or recognise that what you're doing to get each number is adding up the 2 above it. So this last row, it's only the last row in what I'm drawing. So that one just goes there and that goes there. And you can do this indefinitely. So what we can see is if we're looking at a general, hang on, I'm just trying to change the colour of my pen back. We're looking at a general expansion of a plus b to the power of something. We could use Pascal's triangle to write down what the coefficients are. The annoying thing is that really you say this is the first row of the triangle and this is the second row. So you can see that if we want the expansion of a plus b to the power of n, then we have to look at which row do you think? Well, it's going to be, looking here, a plus b to the 4th was the 1st, 2nd, 3rd, 4th, 5th row. So a plus b to the n, we need to look at the n plus 1th row of the triangle. So the other thing you should notice is that the powers of the a's and b's always add up to the power you're trying to raise a plus b by. So let's just take a little look to check that we're absolutely sure we understand why this is. So let me just, I shall have a new page like this, because effectively if we've got a plus b to the n, what have we got? We've got a plus b, and we've got n lots of brackets, both with an a and a b in. So whatever we take out of each of these brackets, and in whatever order, if we've got, say, a cubed, we've taken 3 of those brackets have given us an a, which means the other lot of brackets must have given us the b, so that would be to the rest of them. So in this case it would be n minus 3. So we're always going to start, and we typically start with a to the n here, and then we'll go down by 1 each time. So the next one will be whatever a to the n minus 1 b is, and then we'll go all the way, and then we end up with our expansion with b to the n. Okay, so that's just typically that is the way we normally do it, and when we do this then we can have the coefficients. I haven't written the coefficients in here, but the coefficients, these are just the terms, the coefficients then we can get from Pascal's triangle. So if we take a look at an example, so let me just clear this. So let's have an example question. Suppose we have a question that says expand 2 plus 3t to the power of 4. Well, the first things we notice are, if we're thinking of our binomial expansion, is that we're going to set a to 2 and we're going to set b to 3t. Okay, and the power here, the power is 4, so that tells us we're going to have to look at which row of the triangle? That's right, we're going to have to look at the 5th row of Pascal's triangle. And the 5th row is 1, 4, 6, 4, 1. So if we do this expansion in full, and you've always got to take care when you're doing this, so let's do it slowly. We've got 2 to the power of 4, because that's our a to the power of 4. Then we've got plus, and then we're going to take this first coefficient, 4, and this time we've got 2 to the power of 3. Let me put the times in. And then we've got, what have we got? We should have b, so let's be careful. And we've got 3t, okay? So our next term, we've got the coefficient 6, so we've got 6 times, and now we've got a squared, which is 2 squared, and we've got b, 3t, squared. And I can always be checking that these powers add up to 4, so this is 1, so we're doing okay. So now we're coming back down, so we've got 4 times, and this time we've just got 2, but we've got 3t, this time cubed, and then finally we've got our b to the 4th term, which is 3t to the 4th. And you can actually just work all those out, and it's fine to use a calculator, and you should end up with 16 plus 96t plus 216 t cubed. What? No, I read that wrong. Oh, hang on. Pause. So I've got to go back and do this. What's that term? I'm being an idiot here. Okay. And pause. Eight. No, it's not. 8 times 27. Oh yeah. Okay, so we can write this out in full. You can just use your calculator or do a bit of arithmetic in your head, and we should come up with the answer 16 plus 96t plus 216 t squared plus 216 t cubed plus 81 t to the fourth. Okay, what you do have to do is be really careful with negatives, okay? That's why it can be helpful to put brackets around. So if in this example it had been 2 minus 3t to the fourth, each of these brackets would have been minus 3t to the power of something. And so I'm sure you can see that if this, when this is even, well, all my negatives will cancel out and we'll have a positive term. And if we've got an odd power of a negative number, then we'll end up with a negative. So you just have to be really thorough and careful when you're doing these expansions. So what I suggest you do now before we carry on is just go ahead and try some of the questions in exercise 8A, and feel free to challenge yourself with some of the harder ones. So take a little break, go away, have a look at that, and then come back. Right, okay, so hopefully that was all clear and you managed to get some of the hard questions out there. So that's all very well, so we can use Pascal's triangle to find coefficients, but suppose you had a question that said, what is the coefficient of x cubed in the expansion of x plus a to the 13? Well, you could write Pascal's triangle out and work your way all the way up to the 14th row to find the coefficients. But what if this had been 113? You're certainly not going to write all those out, are you? So what we do is we need a better way. So if we think of what I said before, that the coefficient of the x cubed term, if we think of it, we've got x minus a, we've got all these brackets, 13 of them, all with x's and a's in. And so effectively it comes down to a problem of how many different ways can we get 3 x's from these brackets. So we're going to choose 3 of these brackets to take an x from, and that will be the number, that will be the coefficient in front of the x cubed. So I hope that makes sense to you. So the question is, how many different ways can we choose 3 x's from all of these brackets then? Well, how many choices have we got for the first bracket? Well, there are 13 brackets, so any one of those 13 could give us the first x. And then hopefully you remember from probability that once we've chosen that, how many choices have we got for where we get our second x from? Well, there's 12 brackets left, so there are 12 choices for the way of getting the second one. And then what we've got left with 11 brackets, and we've got to choose one of those to get our third x. So at the moment there's 13 ways to choose the first, 12 to choose the second, 11 to choose the third. But we don't care what order they're in, do we? So if you think of what this will give me several terms where we've got the x's from the same brackets. So let's just for an example's sake, suppose we've got terms where we've chosen x from the first bracket, the second bracket, let me do this, and the third bracket. Well, in our counting here, we've also counted as something different the one where we get it from the second first, and then the third and the first. And that's different again to the second and the first and the third. So you can see that if we were to write all these out, we'd know how many corresponded to the same thing. I'm hoping that you will remember that you don't need to do that, so you can do it to prove it to yourself, but we're effectively saying how many different ways can we order 3 objects, and ordering 3 objects we can do, there's 3 ways to choose the first, 2 ways to choose the second one and 1 way to choose the third. So our answer then for what is the coefficient in front of x cubed in this expansion would be 13 times 12 times 11 over 3 times 2 times 1. Right, so okay, so this is what we've got. And I want you to see that that is the same as, well, I could go 13 times 12 times 11 times 10, and I could go all the way down to times 2 times 1. And if I put that over, we've got our 3 times 2 times 1 that we've got there. Just going to put that in brackets to show you. And then I need to cancel out all these terms. So I hope you can see that this bit here is the same as this, because we can cancel these two things out. So that will cancel with that, and we're left there. So the reason I've written it like this is I'm sure this will be familiar to you. Are you familiar with this notation that we can write this as 3 and an exclamation mark, which we pronounce 3 factorial? And that's just a shorthand way of writing 3 times 2 times 1. So this, if we look at this top line, we can write this as 13 factorial, because we've gone all the way down from 13 to 1, over 3 factorial, and then 10 factorial. Okay, so what we've effectively done here is we've found the number of ways to choose 3 things from 13. So if we were looking at a generic coefficient, so say the coefficient of x to the r in this expansion, we'd be looking at the number of ways to choose r things from 13. Does that make sense? Okay, so if we think of the rth term in the expansion of a plus x plus a to the n, then in this case we want the number of ways to choose r things from n. And you may have come across this in probability before. The notation for this is n choose r, and you should find you have a key for this on your calculator. Right, so hang on a minute, let me move this up. So we've got this, so we've got the coefficient for x to the r in an expansion of this form is n choose r. Right, so there's another way that you sometimes see this written. So this is what you see on your calculator. I'll go back to my pen. So you see n choose r. The way it's more normally written for the binomial expansion, I think, is in this format. You just write two brackets, a bracket with n over r, and you can read that the same way, n choose r. And if we're trying to make a generic formula for this, well, if we, oh, I moved too far, didn't I? Let's move this down a bit. Right, so what have we got? Well, on the top, we've got n factorial. Because remember, this was the number of ways to choose 3 things from 13, so 13 was n. So the top is n factorial, and then we've got r factorial, so that's the number of things we're choosing. And remember, we've got r factorial because we don't care what order we choose them in. And then so this term is n minus r factorial. Okay, and that's something you need to know. So you probably want to make a note of this, and it comes in really handy when we cover probability as well. So n choose r, n factorial over r factorial, n minus r factorial. So now we know this, what I would suggest you do, apart from the very simplest of expansions, is forget thinking about which which row in Pascal's triangle you want, because it gets a bit confusing. Because remember, we wanted for this one we'd want the r plus 1th row. So just think of it in terms of, if you've got something raised to the power of n, you're going to do n choose whatever coefficient you need. So let's look at a couple of examples then. Okay, so let me see. Oh no, before we do that, let me write down what I've just said. Effectively, I've said that a plus b to the n equals, so this is our expansion, it's a to the n plus, and I'm going to write this notation, n1, n choose 1, where we're going to take the power of a down and write b, and then we're going to do n2, take the power of a down again and increase the power of b, and we're going to keep going all the way until we get to the last term, which is b to the n. And this statement, this is the binomial theorem, and this is true for n, and we read this as is an element of or belongs to, it's like a curly e, and I suspect you may have come across this with the double line across there. I've not written it very well. That's called the set of natural numbers, and natural numbers are just positive integers. I'm going to write that again. Remember I said I use that for number? So natural numbers, which are positive integers, positive whole numbers. So this is what this is true for. Just a side note, because I do like my side notes, so I'm actually going to put it on the side so it goes away in a minute. We've just talked about factorials. So let's think about 2 factorial equals 2 times 1. I might as well do 3 factorial above it equals 3 times 2 times 1. 1 factorial is going to be 1, just 1. This has not got to multiply yet. So what do you think 0 factorial means? You'd have a little think about that. It sort of doesn't fit the definition of a factorial, but we do say that 0 factorial equals 1. By convention, we say that 0 factorial is 1. And one of the ways you can think that that makes sense is a bit like when we were working out what made sense for negative indices. We can think the pattern here is we divide by 3, we divide by 2, and so logic says we should divide by 1. So it does make sense, and if you think about it, it has to make sense. We've got nr is n factorial over r factorial n minus r factorial. So if we think of let's think of the nth term. It's a bit easier to think about. So for the nth term, we've got n factorial over, r is n, so n factorial, and n minus r factorial is 0 factorial. And the nth term is going to be in our expansion. That's going to be the coefficient of b to the n. So it needs to be 1, because these two are going to cancel out, and we know the coefficient of this is 1. So it's also the same as the 0th coefficient, but I thought this would be a bit easier to do. So the 0th coefficient is the coefficient of a to the n. Okay, so I hope that makes sense. I did just think of something else to tell you, but I've forgotten what it was. Oh yes, so if we look at this definition here, I hope you can see that it's symmetrical in R, if you like. So we can switch those round. So what I want to say is, so nr is n factorial over r factorial n minus r factorial. Well, you should be able to see that this is the same as n minus r. And if you think about Pascal's triangle, then this makes sense. You've got symmetry on each line of the triangle. And if you think of it in terms of, say, choosing 3 things from our 13 brackets, or choosing r things from our 13 brackets of a plus b to the n, then that's the same. Choosing r lots of a is the same as choosing n minus r lots of b. So that's why we have the symmetry. Okay then, so let's do, I think, another example. So let's clear some of this off. And let me just move this over. So let's do an example. So this is that's where we were, we had this. So for my example, let's try, we want the coefficient, you're being asked to find the coefficient of m cubed in the expansion of 4 minus 3m to the 5. Well, all we have to do is apply this. So what's our value of n? 5. What's our value of r? 3. Okay, so we're looking for, our expansion here says we're looking for 5, 3, and then we've got a squared. Well, in this case, a is 4, so 4 squared, and b is, be careful, so b is minus 3m, okay? So we've got minus 3m. Well, I've got a squared term here, so this must be raised to the power of 3. We should have said that the other way around really. Because this is to the power of 3, the power here is going to be 2 because these powers have to add up to 5. So you can just pop that into your calculator. So put it into your calculator, check you know how to do these. You don't actually need to for this example, but check you know how to do these, pop that into your calculator, and hopefully you will come up with this answer, that this is the coefficient of m cubed when we do the expansion of 4 minus 3m to the power of 5. So that's really quite handy. Okay, before I set you loose on some examples, want to try and do one more that's a bit harder because I know you like to have a challenge. Right, okay then. So I'm going to read some of this out. You're told that the first 3 terms in the expansion of 1 plus ax to the n are, so these are the first 3 terms, 1 plus 35x plus 490x squared. And the question we're being asked, we're told that n is in the natural numbers, and the question we're being asked is to find the values of n and a. Right, okay, so how are we going to tackle this? Well, the first thing we can do is to start our expansion. So we've got 1 plus ax to the n. Well, we're just going to plug it in. So we've got 1 is the first thing because this is just 1 to the power of n. And then we're going to have our next term is n1. 1 to the power of n minus 1, so we can ignore that. And ax, just pop it in brackets. And then our next term is going to be n2. And we're going to have ax squared plus, and then all the other terms that we're not bothered about. You may want to just look in your book. There is a special thing, a special case of when this first value is a 1. And it just makes it all a lot simpler. But have a little look in your book for where it describes that. I've described the more generic case. Okay, so let's just expand this out and we'll end up with 1 plus, well, n1, there's just, the first term is just n, so we've got nax. And what does n2 mean? So for me, when I've just got something like this, I quite like to write it in this form. So we know we've got n minus 1, that's how to choose our two things, over 2. So however you want to think of this, if you want to think of it as n factorial, n minus r factorial over r factorial, that's fine. So put whatever fits for you here. And we're going to expand this out. So we've got a squared, x squared. And then I'm just going to be careful. I am going to keep doing this because otherwise I've made an incorrect statement. If I stopped there, the statement I've made is incorrect. I need to show that that's actually carrying on. So what have we been told then? Well, we've been told that we've got these two coefficients. So we can write those down. So what do we know? We know that NA, this coefficient here, equals 35. And then I'm just going to write this slightly differently. I'm just going to write that as half of n minus 1, a squared equals 490. And so what have we got? We've got simultaneous equations in n and a. So what we want to do is work out how to eliminate one of them from one of our equations. So what I'm going to do with this, I'm going to do a couple of things in one line. So I'm going to multiply both sides by 2 so that I just get rid of this fraction. So just remember that in a second. And then I'm going to expand this out. So here I'm going to have n squared a squared from this bit. And then I'm going to have minus, and then this term is going to give me n a squared. And remember I said I brought the half over, so on this side we'll have 980. And then all I'm going to do is substitute in this, so 35 wherever I get NA. So this is NA, n squared a squared, which I hope you're really familiar now with just NA all squared. So that's 35 squared. And I can use one of these a's to get an NA, so that would give us 35a. And that equals 980. So I'll leave it for you just to check that what you would do here is take 35 squared away from 980, and then you're going to have to divide by minus 35. And and you should find you get the answers that a equals 7 and n equals 5. So obviously when you work out that a gets 7 from this, you can put n back in here, a back in here, and get the answer is 5. Right, so I think you've got enough now to look at the worked examples. So you've got quite a lot of worked examples you can work your way through in sections 8.3. That would make more sense if I did EGs. Worked examples in sections 8.3 and 8.4 in your book, and then challenge yourself. Do some of the easy questions and the hard questions in exercises 8C and 8D, and see how you get on. Good luck.